Let us start principle of mathematical induction. We also call it PMI, the principle of mathematical induction, or we also know it as PMI. This is a really interesting chapter. Now, before going to induction, let us first of all understand what deduction is. I hope everybody is comfortable with these words, deduction and induction. If you just refer to a dictionary or as per the normal English language, deduction is something that you deduce from something general and then reach at some specific conclusion, right? So this is a deduction from something general to something specific, or in other words, there is an idea that you have, and then based on that idea you make some observation, right? So you move from general to specific, or an idea to an observation. But in induction, in simple English language, we can say that we move from something specific to general, right? So we make some cases, right, specific cases, we observe these cases enough number of times, and we induce that if this case happens, the next will also happen, right? So there is some kind of chain reaction. So we reach at a general idea. So we go from an observation to an idea based on those observations, right? So you observe something, then you observe the next thing, you observe the next thing, and then you see that there is a chain reaction, that if this happens, the next will certainly happen. Then you build an idea out of that. So this is induction. Now in this chapter we are going to study about principles of mathematical induction. Now there is a, what was the motivation behind principle of mathematical induction? Let me tell you in brief. This is an interesting thing. What was the motivation behind it? Now, if you have got a rectangular tile, like this, okay, or you can complete this shape yourself. For example, this is a rectangular tile that you have, okay, and you consider this as your rectangular tile for a moment. Now you have got these rectangular tiles and you place them like this, okay, on a horizontal surface. Now if I push the first one, if I push it, now this will fall like this in this direction, right? Now if this gap between this first tile and the second tile is lesser than the height of this tile, right? Now I am pushing this tile like this, okay, this first tile will fall like this, and whether it will fall on the second one or not will depend on this gap. If this gap is lesser than this height, let us say this height is h, and this gap is x, okay, h units and x units. So if x is less than h, right, this distance is less than this, then the first tile will fall on the second, right, thereby pushing the second to fall on the next one. Now this will fall on the next one, the third one, only in case that this gap here is lesser than this. So let us consider all of these tiles are of h height, right, h units. You can choose your units as per your convenience, or you can simply write h units. What I mean is, whatever unit this h has, same unit you will choose for this gap x, okay. So, and this gap, these gaps are also the same, that are x units each, and x is lesser than h. Now you consider, you push the first, it will fall on second, you then the second will automatically fall on the third, third will fall on the fourth, fourth will fall on the five, and it will continue like that till infinity, as many tiles as you have, right? So all of these tiles will start falling automatically. So there is this chain reaction that you have built. This is a chain reaction, right? So for this chain reaction to happen, there were two things that were very important. Now what were the two most important things for this chain reaction to happen? The first thing was that the first tile falls. This was the most prerequisite condition, that this first tile should fall. And now what is the next condition that is important for all of these to fall simultaneously or continuously, or like in a chain reaction? That if any of the tile falls, then the next tile should fall. So if these two conditions are met, let us say first tile falls, and that will make sure that the second falls, right? And second will make sure that the third falls. So first tile falls is my prerequisite, that the first one should fall, and if any of the tile falls, then the next tile should fall. And for that, this gap has to be lesser than the height of this tile. So these are the two things that we have understood by now. Now if I say that the first tile falls, it makes second tile to fall, then the third falls, then the fourth falls. Can I build a general idea out of these statements? I will be able to build a general idea not based on 4 observations or 5 observations or 10 observations or 1000 observations. Even if I notice 1000 tiles, I cannot build a general idea unless I am sure about the 1001st tile. So what can I say? I can select a general tile. Let us say this goes on like this, and there is this general number. Let us select kth tile. Okay, and then there is next k plus 1th tile. Right, now this k can be any number. It can be 1, 2, 3, 4, or any number, right? So we cannot observe each and every tile. So what I have done is I have selected a general tile, which is the kth tile. Now if I am saying this statement, that if the kth tile falls, the k plus 1th tile will fall. If kth tile falls, then the k plus 1th tile will fall. Right, what I am doing is, if I tell you two things, that the first tile falls, second is if kth tile falls, which is nothing but any tile, right, any general tile. So if kth tile falls, then k plus 1th tile falls. Right, now I've told you two things, that the first tile will fall, okay, and if the kth falls, then the k plus 1th will definitely fall. So if I can tell you these two things, or if I am able to prove or observe these two things, then I can make a general statement that every tile will fall. Every tile falls, or this chain reaction will happen, right? Similarly, in mathematics, how do we use this idea or this motivation? That, for example, I have got a statement, mathematical statement. For example, 1 plus 2 plus 3 plus 4, sum of these n positive integers is equal to n into n plus 1 by 2. Now this is a simple idea. You may know where this formula comes from, but right now you are not concerned with that. Let us look at it as a mathematical statement. Okay, and here in mathematical induction we will denote mathematical statements like this, Pn, right, where n is a natural number. Now there is this mathematical statement. If I can say P1 is true, right, or this statement, that mathematical statement is true, this mathematical statement is true for n equal to 1, right? This is one of the things that I will observe. So when I say P1, that means I need only one term from here, right? P1 means only one term is being taken. What is P2? P2 means, for example, in this left hand side, what is P1? P1 is equal to 1. What is P2? P2 is equal to 1 plus 2. P3 is equal to 1 plus 2 plus 3. What is Pn? Pn is 1 plus 2 plus 3 plus up to n, right? This is how you will think about Pn or P1, P2, P3. And when you have to take P4, it will be nothing but 1 plus 2 plus 3 plus 4. Now, if you observe what is P of 1, P1, it is 1 from the left hand side. And if you notice from the right hand side, I'll put n equal to 1 here, 1 plus 1 here, and then 2 here. So it will be cancelled and it will be equal to 1. So for n equal to 1, this statement is true. If you notice for P2, that means n equal to 2. For n equal to 2, the left hand side is 1 plus 2. And what is the right hand side? Right hand side, I'll put n equal to 2. 2 plus 1 divided by 2. So this will cancel out. This is 3, this is 3. So P1 is true, P2 is true. If you check P3, P3 from the left hand side will give you this 6. And from the right hand side, it will give you 3 into 3 plus 1 by 2, which is also 6. Because this is 4, this is 3. 3 into 4 is 12 by 2, 6. So you have checked P1 is true, P2 is true, P3 is true. Till what time will you keep checking? So there comes principle of mathematical induction, that we will check for n equal to 1. Then we will make a statement or a hypothesis. Let me write this once again. The statement is 1 plus 2 plus 3 plus and so on up to n, and it is equal to n into n plus 1 by 2. So for n equal to 1, let us consider this equal to Pn. Okay, for n equal to 1, left hand side is equal to 1 and right hand side is equal to 1 into 1 plus 1 divided by 2, which is 1. So for n equal to 1, this statement is true. The statement is true, or you can say P1 is verified or true. Okay, now this was my base step or basic step, right? Now comes the inductive step. Inductive step or inductive hypothesis, that I'll make a statement that if P of k is true, or let P of k is true, then the truth of P of k should imply the truth of P of k plus 1. What I'm saying is the truth of P of k should imply the truth of P of k plus 1. For example, in case of tiles, if any tile falls, the next will also fall. If any falls, the next will fall. Truth of P of k should imply truth of P of k plus 1. Then we can say that this statement is true for all n belonging to natural numbers, right? Now, inductive step is that I'll assume that P of k is true. So when I assume P of k is true, what I mean is 1 plus 2 plus 3 plus up to k is equal to k into k plus 1 by 2, right? Let it be my equation number 1. Okay. So based on, now this is something that I have assumed, that if P of k is true, then this is the statement, right? Now if I am able to show from this that P of k plus 1 is true, or P of k plus 1 will give me my right hand side, or P of k plus 1, let me write it first for you. 1 plus 2 plus 3, then I'll go up to k and then k plus 1. This is P of k plus 1. And if it comes out to be equal to, if I replace k with k plus 1 everywhere, it will be k plus 1, k plus 2 by 2. If I am able to prove that this is equal to this, then I will be able to say that P of k plus 1 is true, right? And then by principle of mathematical induction, we can say that the statement P of n is true for all n belonging to natural numbers. I hope now, by now you are comfortable with this idea that first I proved P of 1 to be true, right? Now I have assumed P of k to be true. If I assume P of k to be true, then there is this statement which I have marked as my first statement. Now I will try to prove P of k plus 1 as true, right? So what is P of k plus 1? So we will now try and prove that P of k plus 1 is true. So what will be my left hand side? For P of k plus 1, it will be equal to 1 plus 2 plus 3 plus up to k plus 1, right? If I am able to prove that it is equal to something in this pattern, or for example I replaced k with k plus 1, okay, let us first of all see where we reach, right? We have got enough questions to practice. First of all, let us see what will happen to this. Now this is something that I have got for P of k plus 1. Okay, now let us see what I have. I have got only this statement with me. So based on this statement, I will bring this P of k plus 1 in my desirable pattern. Okay, if I am able to do that, then I'll say that P of n is true. So out of this much portion I know is equal to this portion, this statement here, or this expression here. So let me replace it with the right hand expression of first statement. So k into k plus 1 by 2 plus k plus 1, right? This. And now if you see, I can take k plus 1 common, right, from these two statements, and I'll have k by 2 plus 1. And in the next step, what you can write it as k plus 1, and this will be k plus 2 and divided by 2. So if you notice, this is nothing but this k replaced with k plus 1 everywhere, right? So I can say that this implies P of k plus 1 is true, right? Now I have shown you three things, or two things basically. First, that P of 1 is true. Second, that truth of P of k implies truth of P of k plus 1. Hence, based on principle of mathematical induction, P of n is true for all n belonging to natural numbers. This is the principle of mathematical induction. This is pretty easy. Every question will be easy. There is just basic manipulation. You already know your answer, right? What do you want to what pattern do you want your answer in? You already know about that, so it is very easy and you will get full marks in that. It's just that you should be clear with the concepts that are involved. So this statement basically means that if P of 1 is true, this implies P of 2 is true, this implies P of 3 is true, this implies P of 4 is true, this implies P of 5 is true, and you can keep on writing, right? Basically P of k is true, so this implies P of k plus 1 is true. That means P of n is true. This is principle of mathematical induction. Okay, let us move to the questions and then we will understand it more. Let us start with this example here. For n greater than or equal to 1, there is this statement that is given and we need to prove that it is true, right? Okay, so it is mentioned it is true for all n greater than or equal to 1, right? And even if it is mentioned that in some question it is mentioned that it is for n greater than or equal to 3, okay, you don't have to worry about that. You can start your reaction or chain reaction with 3. So you first prove that P of 3 is true, then assume this to be true for P of k or for n equal to k, and then this is assumption, right? Your hypothesis. and then you prove it to be true for k plus 1. If this assumption or this inductive hypothesis implies this, you will say that the statement is true for all n greater than or equal to 3. But in most of the questions it is written n greater than or equal to 1. So let us start with p of 1. Okay, so let's check for n equal to 1. First of all, you can write this statement. Let's say that this statement is p of n, right? So we can write this complete statement and then put it or show it equal to p of n. Now for n equal to 1, what will be p of 1? The left hand side will be 1 squared. Okay, so p of 1 means I need only first term, one term, right? First, if there is p of 2, then I'll take first two terms, p of 3 first 3 terms, p of n first n terms, right? So this is p of 1 that I'm trying to prove. So for n equal to 1, p of 1 is 1 squared, and on the right hand side it is 1 into 1 plus 1 into 2 into 1 plus 1 divided by 6. Now if you notice, this is 1, this is 2, this is 3, so 6 by 6, and it will give you 1. So p of 1, that is left hand side, is equal to right hand side, hence I can say p of 1 is true. So this is my base step and I am done with the base step here. Now let's assume now this is inductive step. Let's assume the statement to be true for n equal to k, or in other words, let's assume rather than writing all of this, you could have written let's assume p of k to be true, right? Both of these statements are correct. Now we have assumed that p of k is true. So if p of k is true, then we can write this statement here: 1 square plus 2 square plus 3 square plus 4 square plus up to k squared is equal to k into k plus 1 into 2k plus 1 divided by 6. So basically what I've done is I have replaced n with k everywhere, right? So if we have assumed that this statement is true for n equal to k, then this will be equal to this right hand side, and let it be my equation number 1. Okay, so we will now prove that p of k plus 1 is also true, right? So, and this fact that p of k is true should imply that this is p of k plus 1 is true. That means we will use this statement that for p of k to prove that p of k plus 1 is true, right? So we will use this statement to prove that p of k plus 1 is true. So what will be my left hand side for p of k plus 1, or what will be the statement? 1 squared plus 2 squared plus 3 squared plus so on, then k squared, and then the next term k plus 1 squared, right? We will prove it to be equal to what? If I replace k with k plus 1 everywhere, or if I can bring this statement in this pattern, right? Only difference should be that k will be replaced with k plus 1 everywhere. Okay, so the result that I'm seeking out of this statement will be on this pattern. The only difference will be that the k will be replaced with k plus 1 everywhere. So let us see. Okay, we will work on this only. We are not writing any right hand side. So let us work on this. We know up to this much, up to k square, based on this first statement, I can write this expression as k plus 1, 2k plus 1 upon 6, and then plus this k plus 1 squared, right? Now if you see, I can take k plus 1 common from this and this statement. right? These two expressions I can take k plus 1 outside. So k plus 1 here, and then I'll have k into 2k plus 1 divided by 6 plus k plus 1, and then I can write it as k plus 1, and this will be 2k squared plus k plus 6k plus 6 divided by 6. Okay, k plus 1, and this is a quadratic, right? So let us see if we can factorize it. Okay, let me write the quadratic in standard form first. 2k square plus 7k plus 6 divided by 6. This 6 we need in the denominator in the result that we are seeking. So what is the result that you are seeking? First of all, I told you in my introduction that you already know your answer. So what is the answer that you are seeking? I am seeking a pattern like this where k is being replaced with k plus 1 everywhere. So I am seeking my answer as k plus 1 into k plus 2 into, now I'll replace this k with k plus 1, so it will become 2k plus 2, right? So plus 2 plus 1 will become plus 3. So this is something that I'm looking for as my answer from here, right? So let me check k plus 1. Now if I factorize this quadratic, right, this will be 2k squared plus 4k plus 3k plus 6 divided by 6. Now if you see, after factorizing, okay, let me factorize it first. 2k if you take common, then it will be k plus 2 here, plus 3 if you take common, it will be k plus 2 here, divided by 6. Now you see this, you can take k plus 2 outside, so it can be written equal to k plus 1. K plus 2 you can take outside, you will be left with 2k plus 3, and then you can divide it by 6. So this is something that you were looking for, right? Or if you get this on the right hand side or this as your result, then you can say that p of k plus 1 is true, right? Or what you can do is, another way of writing it can be that you can write this statement like this, k plus 1, and then you can write this as k plus 1 plus 1, and you can show this as k plus 2k plus 1 plus 1 divided by 6. Now this is something which is same as this one. This is just to show you that we have got the result on the same pattern that we were seeking, or that we desired to bring it on. So now what we have done essentially in this question is, we proved the statement to be true for p of 1, then we assumed it to be true for p of k, and using the equation that we got from here, we showed that p of k plus 1 is also true, right? And that would imply, by principle of mathematical induction, that p of n is true for all n greater than equal to 1. Okay, now we will continue in the next lecture rest of the questions. Okay.